Hello everyone, welcome to From No to Nothing, Ontological Oxymorons. I'm your host, Joel Bouchard, a doctoral student in psychology, and with me today is Mr. Norman Gayford, a professor of English and philosophy. If there's a topic you'd like us to cover on the show, feel free to email us at fromnowheretonothingpodcast@gmail.com or contact us on our Facebook page. After 160 episodes, it can be tempting to think that we've picked all the low-hanging fruit, that we've exhausted the big headline-grabbing, keep-you-awake-at-night concepts like God and time, and now we're reduced to piddly, insignificant ideas like hope. But every once in a while, one of the heavier topics of philosophy eludes us, almost as if it's somehow absorbing and bending light to avoid us seeing it. Well, an accretion disk of future episode material has brought one such monster to light. Today, we're talking about black holes.
Dun, dun, dun. I can just, sort of the 90s movie trailer. You thought you'd seen it all.
yeah, exactly.
In a world.
Yeah. No, I had a little bit of fun with that one. Just poking fun at us thinking
good.
of. I like to tell people that when we started, we were just going to do 10 episodes on the big topics in philosophy, and then we realized, all topics are kind of big topics once you dig into them. So
they are, and if nothing else, we've shown. We were just talking about discipline, right? We've shown that philosophical discussion is a kind of discipline. It's not a rigorous discipline like running on a treadmill, although intellectually it is. But it's something that goes through your life. We're getting older. I'm doing it faster than you are. Back to temporality. But we're getting older and the topics shift, or we return to a topic and say, you know what? We didn't exhaust that topic because you know what? You can never exhaust the topic. And so, yeah, here we are, black holes.
Yeah. And that's another thing that pops up every once in a while is we'll go, we should talk about this. And then we'll find out we already did talk about that. Right. But like you said, the discussion, it never ends. And lots of times when we're thinking about it the second time around, we're thinking about different areas, or the conversation has evolved past what we talked about the first time.
Yes. And this isn't a particulate, granular kind of conversation, because we've been nurturing this sort of connected through line of episodes for the next number of weeks. But in order to get to those, we have to start with this.
Yeah. Yeah. So what is a black hole?
Well, the one-line definition is a collapsed sun that grows so the gravitational power grows so intense that as it's collapsing, light cannot escape from it, and something is created in which there's a horizon at which things can't emerge.
Yeah.
That's nice and vague.
Yeah, yeah. And so it's not just related to stars either. Anything, any gravitational mass, if you had any accumulation of matter big enough, it could become a black hole. So
and one definition says it's a region of space.
Yeah. Yeah.
Right? So there are other names like gravitars, things that sound like they came out of comic books, because they probably did, because a lot of physicists also read and read comic books, but they're wonderful. They're delightful for that. So a region of space where gravitation becomes so intense that no matter or radiation can escape.
And so we know from basic physics that gravity is related to mass. And so, they did the calculations, and in order for the Earth to generate a black hole, you'd have to condense down the entire mass of the Earth into the size of a ping pong ball. So that tells you just how dense a black hole is. And so black holes, if you think about the whole Earth crammed down into a ping pong ball, you go, wow, that's a really high density. And then when you think about the black holes that are out there, the one at the center of the Milky Way is 4 million masses the size of the sun. right?
Mhm.
So 4 million solar masses in this one black hole. You go, it's terrifying, right? It's one of those things where you go, oh my gosh, that will keep you up at night. So,
and then you look at a picture because we finally saw a black hole.
yeah.
First in 2019 and then in 2021. You can't see a black hole. You just see what's happening around it. It's like looking into a fireplace and seeing the most intense, deepest, darkest red and a little brighter yellow around it. But that's just kind of a ring. It's there. It's a maw. And that was really impressive. First, because it unchallengeable proof that a black hole exists. And then another black hole exists. And the idea that there are black holes at the center of many galaxies. Why would they be at the center? Well, there are all kinds of reasons, and we don't have to go into that today, but gee, they're there. And this is where the philosophy starts to happen. But not only about the rules that they seem to break, but what makes them there in the first place. And in the very fact of their there-ness, makes us have to think about ontology and epistemology, what we know, and all those things.
Yeah, exactly. And that's going to be the really big fun parts of the episode that I'm looking forward to. So yeah, we'll quick black hole anatomy, right? So you have the part that everybody's familiar with, which is the horizon, the event horizon of the black hole. So this sphere that if you were looking at it from the outside, it's just purely black. You cannot see anything around it. Anything that crosses through the horizon can never again pass out into the universe. And then around the horizon, you might have an accretion disk of things that are being
pulled in.
Yeah, pulled in and rotating so quickly that the friction that they're encountering is causing them to light up and heat up to thousands of degrees and, emit light. And then down inside the event horizon, we believe that there is a point called a singularity, because at this point, we don't have the physics to tell us exactly what's going on.
And a singularity can be a point, but it also is, a number of physicists also call it a tear.
Right.
In the fabric of space-time. But that brings up all kinds of things too. So point or tear, whatever. We don't see that.
Yeah. So we'll expound on it a little bit more in our next section here, which is talking about the history of it a little bit. When were black holes first theorized? When did this crazy idea that there might be a point in space where that's inaccessible to us? When did that first come up?
In the 1700s, interestingly enough. So much goes back to the Enlightenment.
Yeah.
When you had a various scientists, including Planck, who were coming on the idea of doing what ifs. What would happen if something collapsed into a small space? How could anything get out of it? Nothing could, because it would have to go faster than the speed of light. That was being talked about in 1783.
Yeah.
Before relativity, before quantum physics, before, so humans are amazingly brilliant and just hit on things that seem random, but then start to make their own causal chain. So yeah, we'll start with that. Back further than you would expect.
Yeah, it seems sort of abstract and abstruse for that period of time, and I can imagine that many contemporaries would say so to these guys, right? Well, man, could you have a star the gravity's so high that the light couldn't escape, and people go, what are you talking about? Of course that can't exist in reality. Why even mention it? But yeah, so John Michell was the guy who originally hypothesized about it, and he had some basic calculations to define it, but he was just conceptualizing it wrong. The way that he thought about it was that you'd have a star, and he still has probably the coolest name for a black hole, right? The dark star.
The dark star, yes.
In a world where the dark star.
Yeah. So,
and there was a TV show called Dark Star, and there's all
and so his conceptualization of it, right, was that you could have a star that was so big that it would still be trying to emit light the way a normal star does, but those light rays would try to escape it and then would fall back down to the surface, which we know now is not the way that a black hole works. But his idea that gravity could be so strong that light couldn't escape was sort of that
was a seminal idea.
That was the foundational idea. And so that was back in 1784.
I was off by a year, dang.
Well, and then general relativity came around. So you want to talk about Einstein a little bit?
Yeah, I mean, Einstein, here's a guy who you'd say is a normal guy doing his paper pushing job and all the time working on the back of that paper on these ideas. But when looking at the universe, reading what he read, studying what he studied, being really mostly, I think, I can't say it's the very first idea, and who can say that, but the idea of, well, when everything's in motion, how do you know that time isn't different? Time might be different. Because is the same time for you on a train experienced the way somebody is who's standing on the ground watching the train go by? How are these things related to each other? Relativity, one thing related to another in that circumstance. How does that actually work? And interestingly, he was the first person, well, one of the first people on record, the first person to take it as far as he did on record. And that's in the early 20th century. So he's starting by looking at, all right, what's the watch say? Or the timepiece on the train gives them by this other person. What's that person's watch say? And it's probably going to be different.
Yeah. And so, what I think about, and spoiler alert, we read Carlo Rovelli's book, White Holes, which is going to be next week's episode. And one thing that Rovelli says about it is it's striking. It takes me back to our episode on juicing, right? This idea of jumping outside of the paradigm in order to look at all of the thinking from a fresh perspective. And Rovelli mentions that's the way that most of the advances in physics have come, right? Einstein, and he goes back even farther than Einstein, back to Kepler and some of these other
Newton
guys.
Right. They get out, they crawl outside the box,
right?
Or they jump outside the box. What happens when you jump as high as you can? You're up there for a moment, but then you land flat on your feet again, so you got to jump again. I think that's what juicing really, when we're talking about that, it's not like you get up there and you're just floating above the planet as long as you can, or the box, so to speak. No, you're making a leap. What do I see? Oh.
Yeah. And so, these guys were visualizing things, right? They weren't just expert mathematicians. These were guys who had imagination, and they had the ability to, philosophize and think on a meta level about the concepts that were being addressed. And so, and Finkelstein, who we'll talk about in just a little bit, all these guys had this, there was art mixed into their science, and that is what helped them make breakthroughs. And so, juicing and the example you just gave there reminds me of another part in Rovelli's book where he talks about, when you're trying to make those types of advances, your success hinges upon what you decide to bring with you from the box and what you decide to leave in the box.
And,
right?
And you inevitably decide to leave something in order to carry something. It's like a ballast.
Yeah.
You have to let something go in order to make it's an economy of scarcity, really, a very strange way of saying it. You have to make room for something by letting something else go.
Yeah. So, and again, going back to the fact these guys we think of them nowadays as being expert mathematicians, which they were, but they had other skills that helped them go on. So Einstein's working at the patent office. He comes up with the idea of general relativity, which talks about, exactly that time, and space are relative based upon the position of the observer.
Yeah.
And then a few months later, another, expert mathematician, but who was serving as a soldier, right?
On the Russian front in World War II.
Yes, Schwarzschild. So he comes up with solutions to the equations, and
mails them to Einstein.
Yeah.
In a rather humble way, sort of saying, "I wish I could be there working on this with you." It wasn't that wording exactly, but I'm doing this right now.
Yeah. And so he comes up with some solutions to the equations, and then it sort of progresses that way because although there's only 3 real things you need to define a stationary black hole, right?
Mm-hmm.
You have mass, electrical charge, and angular momentum. There's different ways that it can be conceptualized, and so different physicists come up with different solutions for all the different configurations, which basically just starts to concretize or establish that, these things that sort of seemed like just an oddity, just a weird thing that popped out of the equations, but couldn't possibly exist in reality.
Right.
The more we look at the different angles of this, the more we start to say, maybe these things could exist in nature, right?
Right. And so Einstein and the rest, up through Penrose and Hawking and so on, Finkelstein in between, they're so Einstein's also conceptualizing with relativity the idea of gravity, because gravity, I can't begin to, I'm not a physicist, but gravity to Einstein was the thing which held everything together, essentially, right? So if a bigger mass or a more substantial density exists, then it's going to bend the fabric of space. And if you bend space, you bend time. And so from Einstein, we get the idea of gravity wells. In science fiction, that's used all the time now. Here's a ship and it gets caught in a gravity well and it's getting pulled in. Well, it's like a swirl in the water in a creek. We can see something visually like this. And so what happens if a well is so intense? Well, then it's pushed way down inside, because you visualize the universe as a thing of a balloon, right? If it expands, it stretches, things get wider. Well, what happens if you put your finger into that balloon? And that's kind of like a gravity well. And so.
Yeah, no, exactly. And I think that's a good way of highlighting some of the problems with conceptualizations of black holes, is that, so they pop out of the equations of general relativity. And so Einstein had conceptualized and that, space and time were one thing, space-time.
Mm-hmm. And
that, black holes were a gravity well, just like you said, which is a bending of space-time. And then around the same time, early in the 20th century, and then throughout, up until the present day, quantum mechanics has looked at it differently. And rather than saying, okay, well, there's just this space-time fabric that's getting bent, they're saying, no, there's a granularity to reality. There's constituent elements. There's a spot below which you can't go any further. There must be some particle, some quark, something that constitutes space itself. And long story short, over the past 100 years, physicists have done testing both theories, saying, well, they can't both be right, so we'll figure out which one's right. But the more they test them, the more each one gets a higher and higher precision and accuracy, and gets more and more established as providing us accurate predictions, right?
Mm-hmm.
And so the physicists at the point in time in which we're currently hosting this podcast, they're very confused, right? Because they're going, man, both of these things, they just keep getting more and more accurate at predicting what we see, but they're mutually exclusive. So we have to find some theory that unites
pulls them together.
Yeah. Yeah. And so that'll play into some of the issues that black holes have that we'll talk about in a bit.
Mm-hmm.
But yeah, Chandrasekhar, an Indian physicist in the 1930s, he established the, not the exact, but the mass at which a body collapses into a black hole.
Mm-hmm.
And so, and Oppenheimer, who, developed the nuclear bomb and things, they defined it further and had the reality of neutron stars pop out of it. And so we're discovering new bodies, neutron stars, and maybe even beyond that, quark stars and
exotic things.
Frozen stars is what one conceptualization they had, which is where when it collapses into a black hole, the point at which the star collapses but crosses the event horizon gets frozen in time there. So you only see, when you actually see a black hole, what you see is just the star at that point of collapse forever, right? And it never moves, it never changes.
Yep.
So all these different ideas swirling around. A lot's popping out of it. David Finkelstein, who we talked about earlier, and who was a huge influence on Ravelli, talks about how his ideas regarding black holes pop out of Albert Durer's woodcuts.
Yeah,
right.
So
Again, art and science.
Albert Durer's woodcuts from the 1500s, and here's a physicist, a mathematician, who says Durer's piece, Melancholia, shows us what happens when you try to have total perspective. You can't. There's an ambiguity that's created. That's what. Well, side note, that's why we need humanities in education, because it advances other things. We need it because we need it to be creative, but we need it because it also pushes people, juices people, leads them to epiphanic moments. You can't create an epiphany.
Right.
It just happens. You also can't stay within it. So, yeah.
And so we start to see some things in nature that point towards the existence of black holes. Jocelyn Bell in 1967 was building a radio telescope with a renowned physicist at the time. And she starts noticing these really fast, very rhythmic sounds that are accurate, within a very tight window. She goes, you normally don't see a repeating pattern like that. Finds out they're pulsars, right? Out there's these husks of dead stars that have radio jets shooting out the poles. And each time you hear one of those clicks, it's one of those poles flashing in front of Earth and hitting the radio telescope. And there's dozens of times a second. It tells you how fast these things are rotating, because they used to be so big and diffuse, but after they collapsed, much like an ice skater pulling their arms in and starting to spin faster and faster.
Yeah.
They're spinning every second. You go, okay, man, it's really starting to look like maybe there's something out there. And then Roger Hawking and Roger Penrose and Stephen Hawking, they come up with Hawking radiation. Hey, well, these things might emit some kind of light. And Cygnus X1 was the first black hole discovered. And again, like we talked about, we did not see a black hole, and you cannot see a black hole, but we finally had an image of one in 2017. But all the way up until that point, there was still quantum physicists who were saying that they didn't exist, that you could explain them theoretically. You could explain the phenomena theoretically in such a way that you did not need a singularity, you did not need a black hole.
Mm-hmm.
And they were sure that when you pointed the telescope there, you would see something different. Isn't that wild? Right? All the way up wild. Until, the moment that the picture was taken. And of course, we were vastly simplifying that. The picture was taken by a global, essentially a network of cameras and satellites, the size of the Earth, over a long period of time, and then the data had to be collected and
Right.
aggregated and interpreted.
It's not taking a picture with your cell phone.
Yeah.
And the distance that this thing would be at, trying to see it, one of the analogies that's often made is that to see that one is essentially like trying to take a picture of a donut on the moon.
Yeah. Yeah.
Speaking of donuts, we were talking about that earlier today. So yeah, this is not simple to do.
Yeah.
But the instruments are.
So yeah, 2017, we get a photo that clearly shows, well, what looks like a donut. A black circle with a reddish orange ring around it, which is the accretion disk we talked about earlier. It's the black hole at the center of M87. Which is just pulling in matter, and the friction is heating it up and causing it to glow and emit light as a plasma and reach our eyes. So that's sort of the history of black holes.
Yeah.
So now we'll get into the real interesting stuff, right? What are the philosophical questions raised by black holes?
In no particular order. And what I miss, you'll fill in. We'll do it back and forth. The fact of their existence when the idea was that they couldn't exist affects people who are determinists. It affects the idea of determinism because if everything is already predetermined, then when you have something like Einstein's theories, and they come to pass in the hiss of the explosion of the Big Bang, and they come to pass now in seeing the black hole, it means that other things probably will come to exist too. It affects two isms that we haven't, I think a couple of times we alluded to them. We didn't talk about them, I think, in a separate episode, but presentism and eternalism. And presentism is essentially a philosophical viewpoint that the only thing that exists is what exists right now. It's obviously more than that, but that's a start. We'll come back to it. And eternalism is that everything exists, whether we can touch it, whether it's an object. Now it's an object in our head. We created it, it exists. Rome existed as an empire, and so on and so on. Well, the problem of the black hole really puts a dent in presentism from the viewpoint of some scholars and physicists. Romero is the one I've read most recently. 2022 article in a journal called, I believe, Critica, a Mexican journal, and a science journal, well regarded, cited in many places, in which he essentially takes presentism down a peg or two.
Yeah, you can see how it becomes an issue, right? And maybe we haven't spelled it out clear enough yet at this point, but so if you have a gravity well, so it's warping space, and it's also warping time, because space and time are one thing, as Einstein has demonstrated. And this isn't just theoretical, right? We can, the GPS in your car would not work if this were not true, right? Because it's outside of the gravity well, so things wouldn't line up correctly. Well, what happens is if you have a gravity well that's so strong that light can't escape from it, the closer you get and the more gravity you feel, the more time slows down, because time and space can no longer, they're getting sucked into this well, right? So if you were getting closer and closer to this black hole, and you were looking outwards, so you're going towards the black hole with your back towards it, all of a sudden you start to see some weird things, right? The stars in the sky that are usually stationary would suddenly start moving. They'd start moving faster and faster, right. And then things would continue to speed up. And essentially what would happen, right, is there's no local disturbance or difference to you, right? If you cross that event horizon, or if you're very close to it and you look at your watch clicks normally. Time continues on as it always has for you. So your present moment continues to be what it is. But the outside world that's farther away from the black hole, suddenly you start to see its future. Or rather, you start to see its present moment be accelerated, right? To the point where if you don't cross the event horizon and you decide, okay, I'm going to paddle on back to Earth or wherever you went, everybody that you knew would be much older or would be dead. You'd be into the distant future. And so even though, so many hours or years had passed for you, many, many times that amount of time would have passed for everybody else.
Yep.
So for a presentist paradigm to say, well, the present moment's the only thing that exists.
Yep.
Well, that's an absolutist position rather than a relativistic position. And we know that in regards to time, the relativistic position is the correct one scientifically. So it's really hard to defend presentism. At least on you might be able to develop an abstract relativistic argument for it.
You might be able to, and there's a different level of presentism, which is just the cultural, but it also it also seems fluff is not the right word for me, because I don't want to be insulting, because people work very hard at the idea, but the idea of presentism in that way is being uncritical, adhering to the values, so to speak, or the structures, the attitudes that we have now, and to interpret everything in the past, because presentism indicates that there's a past. It's just the past is gone. It's there's not a lot of relevance. But if we look at the past, we see it through our eyes now, and the presentism kind of asserts that that's the only way you can see it. You can't unbe who you are. I think there are problems with that too. Of course, it's the whole idea of objectivity and subjectivity, related philosophical concepts. What you just described in coasting toward the black hole, or indeed if somebody's back on Earth and somehow is able to watch, their sense of how you're moving is going to change and then you just wink out. So objectively, who's right? Well, objectively, there isn't, because you're subjectively, your time is 10 o'clock a.m. as you're at the event horizon. Subjectively, perhaps, back there on Earth, it's the same thing, but it isn't.
Yeah, and that's where, I think that the deterministic issue comes in, right? Is because if objectively the subjective viewpoint is the only accurate one temporally,
mm-hmm.
and if we are able to change that, to modify that, then how you could zoom out and have a clear picture of the universe is sort of tricky. But this is what physics intends to do, right? The goal of physics, right, is to view the universe materialistically and to establish a set of preconditions under which things have developed the way that they have, right? So in theory, you should be able to look at preconditions and be able to predict anything that's happened in.
Well, yeah, and astrophysics, to me, astrophysics itself, as a layperson, seems to me that it supports the idea of eternalism, of the idea that everything exists, because we know that when the age of the universe gets bigger and bigger, and we see more and more with our telescopes, we know that those stars that we're seeing, if we saw a star from 13 billion years ago, that star's not going to be in the same place. That star's probably not going to exist. What was there is no longer there, but it's there because we can see it, but it's not. So we have this possibilism of we're seeing the past, we're in the present, we're extrapolating into the future. We're looking at a galaxy at a distance and extrapolating its future into what it would be now because of the closer galaxies that we see in their relationships. So presentism doesn't really hold.
Yeah, and that's a tough thing for people to wrap their minds around, is that telescopes are actually time machines, right? You're not just looking at something that's far away. You're looking at something that's in the past. But whose past, right? Because like you said, it's our present. So I am in the present, but I'm seeing something that no longer exists, that hasn't existed for billions of years. It's been extinct, right? It's been gone. And again, this is all modified by gravity, by effects on space-time. And sometimes astronomers will use that to their advantage. If there's a black hole in front of something that they're trying to view.
Something called lensing.
Yeah. They'll get gravitational lensing, and it'll form an Einstein ring, right? Which will actually allow them to magnify what's behind it and see much farther than they'd be able to. Because
take a drip of water.
Yeah,
right. And look through it.
Except with space and time, right? Being so it's really a really strange phenomenon that's hard for people to wrap their minds around. But so black holes are wildly philosophically
presentism, eternalism, ontology, being. Does it exist? What does it mean that this exists? Was this thing always going to be there? Was it determined by the conditions of the universe to be there, or are things changing in such a way that an indeterminist view makes more sense? And that's just the start, because then just within physics, you have people who are trying to make things accurate, say, well, if this exists, then this must be what's happening, like Ravelli, inside a black hole, by what we know now, but we're not certain. So are our instruments accurate enough? And how do we create the most objective instrument? And how does the conditions of what we've found that we didn't think really probably existed, how does that change what we do to our instruments? And
so we'll look at black holes a little bit more in depth, because a lot of listeners, the big thing to them is the event horizon, right? And so in some ways, I think that might be, black holes are fascinating. Every part of them is fascinating, but to me, that might be the least interesting part, right? I think that the temporal and shift, the closer you get, the gravity changes and what that does to the outside world is very interesting. But you reach the event horizon. If you're a human, you're an astronaut, right? The first thing that happens is you're just going to get shredded by the accretion disk in most stellar mass black holes, right? They're spinning very fast. They have high charge, angular momentum.
You're not going to get a ship through it.
Yes, there's stuff falling into them that is the friction is moving so fast that it's turned into this white hot plasma, and so you're going to get killed that way. If there's nothing else getting sucked in, right? So there's no matter, no accretion disk for you to get destroyed by. If it's a small black hole, you're going to get spaghettified, which is where your head, if you're falling in feet first, right? Your feet are going to get stretched far, far out in space and time. So you'll get very, very tall and you'll get ripped apart that way. And again, a very strange effect, but just to think that the space between your feet and your head, right? That the gravity could be so high that it would start to pull your feet that much faster than your head to stretch you out is very strange. But as Ravelli says in his book that we'll talk about next week, that's really not any different than what happens when you drop a rock here on Earth, right? You could do the math. It'd be very, very hard because of the very slight effects of Earth's, gravity compared to a black hole. But essentially, when you drop a rock, it's not just gravity pulling it to the ground. The rock is traveling also through space and time, right? Mm-hmm. And that this again we've talked about it in the past where, if you try to find the center of the universe, what you'll find is that you are the center of the universe, right? And so if you are the center of the universe, which again, this it goes back to our conversation about nowhere, right? About temporal locations, coordinates.
Mm-hmm.
If you are the center of the universe, the center of all space, well, and if space and time are one thing, then you are the center of time, meaning that your present moment, right, is the present moment, and you are at the center of the universe. But the other thing that brings into account is that you are, and everybody else is also at the center of the universe, and their present moment is also the center of time.
Yep.
So if you try to take the measurement and it says it's where you are, and if somebody else tries to take it and it says it's where they are,
it's right.
And yeah, and so and if the rock is dropping, right? The rock is traveling through time. We don't think of that because it appears to all be in our present moment. But we've talked in the past. What constitutes the present? How long is the present? Is it a second? Is it a millisecond? Is it a Planck length? What constitutes the present, right? So these are the interesting.
And you have to define that. If, as a physicist or as a non-physicist, you engage in definition. The very point of engaging in a definition means that you've attempted an isolation. You've attempted a frame. Many things are going to escape that frame. You know it. And so the definition doesn't work quite right. So you modify the definition. And by so doing, how you take in information is going to be changed. And all that's built into a black hole because of the idea of information with black holes. Hawking was suggesting that no information could ever leave a black hole, but that, and his views changed too, but it takes us to the word information. What does that really mean?
Yeah.
If it is a thing, then it is an object, and objectivism has to hold. It means it's material. It means, okay, then space-time is a material. Why? Because it can be heated up. Can information be heated up? No. but that which information is stored on can be.
Yeah. It really starts to get crazy with the space-time dimension.
We're spinning.
Yeah. So you attempt to cross the event horizon. The first time you get destroyed by an accretion disk. The next time you get spaghettified because the black hole is moving too fast and is too small. Let's say the conditions are just right? You find a huge supermassive black hole.
That isn't rotating.
Yeah, so counterintuitively, right? The bigger the black hole, the less scary it is for you as an astronaut, right? Provided it's not rotating. There's no accretion disk, right? It's just sitting there very nice and calm. And you reach the event horizon. To your surprise, you are not instantly killed based upon the definitions I've given already. You cross the event horizon. This is possible. You could cross the event horizon of a calm, supermassive black hole and not die. And your time would continue to tick by as it normally does. Now,
the outside world.
Yes. So the observer, this all depends on the observer location, right? Once you cross the event horizon, you can never go back out. And not only that, but the space and time stretching that you saw when you were on the outside intensifies. It continues to intensify. Once you cross the event horizon, you will be taken to the center, the singularity, or whatever is down there. How long that takes can vary. Some estimates say a few fractions of a second. Some say maybe a couple hours, maybe a few hours in a really big black hole. But eventually you'll get to the singularity. And during that time, and during your trip, time outside the black hole will continue to proceed faster
so billions
and faster
of years
and
could
faster.
have passed in the 2 hours it took you to get from the horizon to the singularity.
And so this is where Penrose and Hawking's work becomes very interesting, right? Because up until their time, we thought that black holes were just going a permanent fixture, right? So the star collapses, nothing can get out. And so the black holes will just continue on to the end of the universe. Well, Hawking and Penrose came in and said, no, due to quantum tunneling effects, and quantum entanglement, where particles pop in and out of existence, there are things that are just inside the event horizon, right? That there's just particles that are going to eventually pop out. And through that, the black hole will eventually evaporate. It'll disappear. So with that little tidbit of information in mind in our journey through the event horizon, you suddenly realize, okay, well, if I cross through the event horizon and time outside continues to move faster and faster and faster, eventually the point at which this black hole evaporates and disappears approaches faster, right?
Yeah, yeah.
And so as you reach that horizon and the black hole is dissipating, something happens, right? Or rather, perhaps something doesn't happen. Perhaps all things cease to happen. And that's where what we highlighted earlier, the problems between quantum mechanics and general relativity really become difficult, right? Because general relativity has been around for so long and it explains so many things well. But it's the general view of physics that it must be wrong because there's affinities in the equation, most notably at the singularity, which is highlighted as a point of infinite density. And therefore, as you can extrapolate from our conversation, if the density is infinite, then at that point, space and time cease to exist.
Right. Entropy is reached in a sense.
Yeah. So if we cross the event horizon and then we make it to the singularity of this black hole, we reach a point where time stops, space stops. So what actually happens there, right? And this has been the stuff of science fiction and
all kinds of
daydreaming forever. But the view of physics is that there's no point in all that science fiction. There's no point in all that daydreaming because a singularity cannot exist. And so quantum mechanics has tried to come up with different solutions for what's at the center.
You captured that very well with doing all the equations on the blackboard. I want to caution anybody about this ahead of time. If you go to the Stanford Encyclopedia of Philosophy and you read the article on singularities and black holes, it's fascinating, but it's probably the most dense, appropriately, one of the most dense pieces that you can find in that online tome. It's worthwhile. It gives you a humility of the size of things, but it's not for the faint of heart.
Yeah. So right now the listeners are probably saying, yeah, but we want to daydream. We want to talk about singularity. And they're thinking, well, we're pretty late in the episode. Are we going to get to do that? Don't worry. Next week, when we talk about white holes, we're going to do a lot of it.
Yeah.
But I think at this point, it's good to ask, how do you think our conception of not just the universe, but reality itself would be vastly different if black holes didn't exist? What if they didn't exist? They weren't out there, right? We did the equations, and guess what? Everything's Newtonian. There's no need for all of that. How do you think that would impact us philosophically?
I think it would remove some, not all, or maybe even a lot, but it would remove an essence of the bizarre, the unknown, the infinite possibilities. And this is going to sound really strange, but black holes are part of the keyhole into doorways to other universes, possibly. They help to speculate on sub-universes or bubble universes or tunnels between time and other places that if they didn't exist, if they were proven that they didn't exist, then we might well be I don't know how quantum physics would go with it, but we might well be in a place where we say, okay, one universe is enough.
Yeah.
Or time really is manageable. It works in this way, and yes, relativity of functions, but sooner or later we're going to see to the end of the universe, and sooner or later we're going to be able to measure everything. And I think it removes that not arrogant, but could be arrogant certainty that we can nail everything. It takes me back to there was a time before the turn of the 21st century when there were some historians, some few, who really had their bubbles burst, who were writing about the end of history. When the Berlin Wall fell, communism was going to fall, capitalism wins the entire planet, everything settles down into capitalistic exchanges that bring us into some kind of strange utopia of buy and sell, and the whole planet will be just fine. No more history because there's no more conflict. And it was, I remember laughing myself silly reading this back then. And we certainly see how that hasn't happened. But I say that because I think that that's the nature of, when you look at physics as a layperson and you read about quantum physics and you say, black holes exist. I can see one. They've put it in front of me. Okay. That means that time is really wild.
Yeah. It's just, it changes everything. Right? I think what it comes down to is nobody wanted black holes to exist, right? I don't think any religious people, any theistic people, I don't think any scientists, Einstein himself, right? He wrote paper after paper trying to convince other physicists who were, can you imagine that? Like you come up with this thing and then people are like, oh yeah, and by the way, here's the thing supporting black holes. And then you're like, no, this, it cannot be, right? So nobody wanted this, right? Because I think that if you go back, before relativity, I think that physics was sort of in a similar place. The end of physics was kind of never in sight, right? Because there was too many unanswered questions, and there always will be. But there was a point where you could go, okay, like you said. I mean, at that point, we didn't even know that there was more than one galaxy, right? We sort of thought
in my lifetime, the universe has expanded immensely,
right? And so you could imagine if everything was Newtonian, you could say, okay, well, there's a pretty clear arrow of time, and it's quite straight, never bends, right? It's made out of a hardy material, and there's no reason. Yeah, exactly. Well, I think then it becomes very easy for the physicist to say, well, now we can just trace everything back to initial conditions, right? We can establish a few conditions and then just watch the way things have expanded, and we can explain it. And creationists could say, hey, listen, like, again, the arrow of time, right? I think it's time.
It is time.
And space is obviously a part of that, but I think that from the ontological point, right? And that's the big thing. I think that how black holes change our reality is, ontologically time related, right?
If time can stop, if time can be reversed, if time can exist in multiple facets all at once, if you could see yourself in a variety of ways as in a house of mirrors, but that's what it looked like all the time to you, you'd probably go mad. But we already knew that time zero, even with Einstein, made this happen. The arrow bends a little bit if it gets too close to a planet. If you leave a planet and you go to the moon, this was measured when the Apollo astronauts first went to the moon by increments. Their timepieces were different. They kept slightly different time than back on Earth. So we already knew that time zero had various speeds, but we didn't know it could be reversed. We didn't know it could be bent. We didn't know it could exist at the same time necessarily. And so, yeah, time is the thing.
And that raises all of the big questions about, I think that what it comes down to is fundamental versus attributional properties of reality, right? And I think that up until relativity, humans that assumed that time was a fundamental aspect of reality because it always proceeded so predictably in our day-to-day experience.
Yep.
But first mathematically, and then through a variety of theoretical perspectives, and then through observable, concrete demonstrations, we have seen that that's not true. That time is relative. And I think that raises so many issues about, well, now what does that do to our experience, right?
What does that do to our, and that goes all the way from the spiritual to the religious, and to every passage you can think, because black holes also mean the probability of singularities, since the black hole is singularity is a tear in space and time. I mean, you can look at charts. It's in the it's in the articles that people write. So a path goes up to this tear and goes into the tear, and then what? Does it come out another side? Does it come out somewhere else? How can a path just stop?
Yeah, that's the interesting part about it, right? Is that, again, just the weird, wacky way that this worked out. The gravity is so intense that you must reach the singularity. There's a 100% chance you cannot escape. But then when you get there, everything that we know about math and physics says that we essentially don't know what happens, right? Time ceases to exist. Space ceases to exist. And then the quantum aspects, many interpretations of them, and again, we'll talk about this next week, but many interpretations of them don't really help the situation. They all say, man, there's really no way around it. You reach the singularity. It's not as if time and space come to a standstill. They cease to exist. There's nothing there anymore, right? And that's where really interesting things start to pop up, where they go, well, okay, well, when we look at the cosmic microwave background radiation and we look at the Big Bang, man, a lot of that, the mathematics are the same as a black hole. Could it be that we are living inside the event horizon of a black hole in another universe? Do the black holes in our universes go to Big Bangs in new universes, right? Is there a strange multiverse through which we have these wormholes that take us to these places that we can't travel through, right? It's not a science fiction thing, right? Where a human could fall in and come out into a different place. But something might. Something could.
And when you come to that place again where you ultimately say, we don't know, I think this is the most important, for me, moment, if you think spiritually or philosophically, both, any number of things. Fundamentally, no one knows what happens next. We have religious texts that say with some vague certainty, well, yeah, this happens. We don't know. That doesn't mean you stop being a person of faith if you are a person of faith, or stop being explorational with spirituality if you are such a person, but it ought to energize it and excite it because it's clear we don't know.
Yeah. Yeah, and I think that's the ultimate consequence of black holes existing in the universe, is that it just caused everybody, regardless of your faith or your preconceptions or your views on scientific reality, it caused everybody to go, man, now we don't know. And not only now do we not know, but there's a good chance we may never know. And then it puts the human experience into a whole different category than it used to be in before.
Yes.
But yeah, I'm super excited for next week's discussion and for the following weeks. Like I said, we'll probably look at 4 or 5 different concepts in this kind of short series, but they're all going to connect. They're all going to be really interesting, and I'm excited for them. So until next time, keep on.